So last week we have been working on the equilibrium of a particle. We consider the free body diagrams by isolating a particle and then representing all forces in the particle, and then we write the equilibrium equations for the equilibrium of a particle. Summation of forces in the x direction equal to 0. We have one equation. Summation of forces in the y direction equal to 0. We have our second equilibrium equation. And then we solve these equilibrium equations for the unknowns we are looking for, right? So we did that last week. This week we are going to start the equilibrium of 3D rigid bodies, which is a bit more complicated because we need to introduce one important concept for that, which is the moment produced by a force, all right? So for example, if I have this force F, this force F, for example, is applied at this point A. If I want to evaluate the moment produced by this force about, for example, this point B, okay? So what I have to do is, so what I'm looking for is the moment at point B that is produced by this force F. So what I have to do is I have to, first of all, I need to connect point B with point A with what we call a position vector. We usually call this R. And then we have these subscripts RBA. It means is a position vector connecting point B with point A. All right? So, and then of course we need to have a coordinate system. Let's say we have this coordinate system X, Y, Z. All right? Because we are working with vectors, we need to have a coordinate system to obtain the components of these vectors. And then the moment produced by this force F is given by the external product of the position vector connecting the 2 points, the point B, where we want to evaluate the moment, and the point A, where the force is applied. And we need to do the external product. We talk about the external or the cross product with the force vector. Right? So this is, by doing this, we obtain the moment produced by force F. And this can be easily done by writing now the vectors. I can say that my position vector will have a component in the x direction, a component in the y direction, a component in the z direction, right? And my force vector F, same thing. It is going to be a vector with a component in the x, y, and z directions. Okay? And then the only thing I have to do is the cross product. So the first what I do is I consider this cross product here. So for the x component, I consider this cross product, right? Oops. So I will have RYFZ minus RZFY. This is my x component. My y component, for the y component, I need to do this cross product here. So this one times this minus RXFZ. So I will have RZFX minus Rx Fz. And the last one is this cross product here, right? Which will give me Rx Fy minus Ry Fx. And this is the result. This is the result of my moment produced by force F about point B. And as you can see, this moment is also a vector, because we know the result of a cross product is a vector with component in x direction, which is this one. This is my component in the x direction. Component in the y direction, which is this one. And component in the z direction, which is this one here. So I can say that the result, so I'm going to put it in red here, the result of this cross product is going to be a moment which is a vector, and so I will represent this vector like this with two arrows at the tip. At the tip, if we put two arrows, we know that it is a moment. Some authors, they represent in a different way. They just write the vector and then they represent like this, which means a kind of a torque, if you want, for a moment. But I prefer to use this notation here for, so basically it's a vector with two arrows at the tip, so you know this is a moment. Okay, so if we focus on 2D, for example, imagine I'm doing a two-dimensional problem now, 2D. So I have a force like this one. Let's consider a very simple case where I have a vertical force F. Okay? And then so let's say this vertical force is applied at point A, and then I have point B here. So this is going to be my position vector, RBA. I want to calculate the moment at point B. Is my question. So let's assume that I have here a generic angle between these two vectors. Let's say, imagine this angle here. No, this is not very good. Imagine this angle is a very generic one. I will say alpha. Okay? We will have a coordinate system. I will say this is my x-axis. This is my y-axis. Are you guys following this, or yes?
When you say by moment, what do you mean? Because it's 2D.
Yeah, 2D, but the moment is going, if you think on the cross product between this position vector and the force, they are both in the xy plane, right? So from the property of the cross product, we know that the result is a vector that needs to be perpendicular to these two vectors, the position vector and the force vector, right? So it means the moment is going to be a vector which is aligned with the z direction, perpendicular to this 2D plane, right? Yeah. And I'm going to show you that by doing the cross product. You are going to see the result is going to be a vector which has direction on the z axis only. If you are doing a 2D problem, yes. If your z is the axis perpendicular to the plane, then it will have component on the z direction only. But I'm going to show you right now, okay? So in order to do that, let's say, let's assume this angle alpha in this case, in this example, is 90 degrees. Just to make things simple. So if I calculate my moment about point B, I'm going to write first, I'm going to write the position vector, this one in green, okay? The moment is always the position vector cross product with the force vector. So the position vector, so I'm going to say the moment is going to be RBA cross product with the force vector F. Now I need to write the position vector RBA. So in this example, I made this in such a way that the position vector is aligned with the x-axis. So I only have a component in the x direction. I will call it RBA. Then in the y direction I have 0. In the z direction I also have 0, right? So this is my position vector, only a component in the x-axis. Now I need to do the cross product of this position vector with my force vector. And in this example, my force, I made it aligned with my y-axis. So it only has component in the y direction. So I can say that my force vector is 0, F 0, right? And now we just need to do the cross product to obtain the x component first. X component, I need to multiply this 0 with 0. It is equal to 0 minus 0 times F, which is also 0. Agree? So x component is 0 of my moment. For the y component, I need to multiply this 0 with this 0, which is 0, minus RBA with 0, which is also 0. So my y component is also 0, right? And for the z component, I have RBA times F minus 0 times 0. So I have RBA times F. As you can see, now this answers your question, right? As you can see, the moment, the vector moment, only has a component in the z direction. So even if you are doing a 2D problem, the moment will always be perpendicular to that 2D plane, or in this case, if the z direction is that perpendicular direction, the moment will have only component in the z direction. All right? So let's keep this. So I'm going to do this now in a different way. The moment in 2D we can do in a different way, in 3D as well, but it's much more complicated. But I'm going to do. So what I'm going to try to do, I'm going to try to copy this figure here. Let's see if I can do it. So copy. And then I'm going to paste it here, let's see. Perfect, right? So let's do the same example, which is calculate the moment about point B. But now using a different technique. So we know that this moment is going to be a vector in the z direction. And we know that this moment is calculated from the external cross product, right? RBA times F. We know this. So what I'm going to do is, what about if I want to know the norm? The norm of my moment, or basically what I'm saying is that what is the intensity of my moment? Well, from the definition of the cross product, if you have a cross product, the norm of a cross product is equal to the norm of the first vector, RA in this case, times the norm times the norm of the second vector, which is the force, times the sine of the angle that is made between these two vectors. So position vector, RBA, and the force vector, in this case, they make an angle of 90 degrees. but if you think it in a general way, we can say the angle between the position vector and the force vector is given by alpha, a generic angle, right? So, if we do this way, we can obtain then the norm or the intensity of my moment. And then, if we apply this to this case, where this angle alpha is 90 degrees, we have what? The norm of RBA is our RBA, right? Is the length, basically, is the length of this position vector. Sorry, I did something wrong here. I included the vector. Of course, there's no vector here. This is the norm, right? So this is a scalar, RBA, which is this length. So I can say this length here is my RBA, right? The norm of my force F is the intensity of my forces, 100 newtons, 500 newtons, 1,000 newtons, whatever, right? So basically, is the length of this vector here. I will call it F, which is the norm of F. And in this case, alpha 90 degrees, so sine of 90 degrees is equal to 1. So this is what I get for the norm of my moment, right? And you can see that this result, RBA times F for the norm, is exactly the same as the one we obtained here. RBA times F is the same, isn't it? So by doing what I want to tell you is that by doing the cross product, we obtain everything we need to know for the moment. We obtain the norm. We just need to calculate the norm of this vector. So if I want to calculate the norm of my bending moment, the norm is the square root of, in this case, 0 square plus 0 square plus RBA F square. So this is equal to RBA F. This is how I calculate the norm of a vector, right? So by doing the cross product for the calculation of the moment, I have all the information I need. I have the norm or the intensity, and I have the direction of this vector. In this case, the direction is the Z direction. By doing in this way, in 2D problems, I can calculate easily the norm of my moment. This what we did only gives me the norm, but the direction, I need to know the direction is perpendicular to the 2D plane. Right? In this case, Z direction. So this is, you can do this way if you want in 2D problems, because 2D is easy, but to do this in a complex 3D problem, I strongly recommend you to do directly the cross product, because everything comes out automatically. Yes, someone was asking.
Why is it going in the Z direction?
Sorry?
Why is it going in the Z direction?
Why is it going in Z direction? Because last week we talked about cross product, right? Yeah. And we concluded, I can write here, we concluded that if I have a vector, in this case RBA, which is aligned with my x-axis, right? As the same direction as x, agree? And if I have a force vector, F, which has the same direction as my y-axis, so when you do this cross product, RBA, cross product with F, that will give you a bending moment, in this case at point B. This is my point B, right? Sorry, not the bending moment. I said that will give you a moment at point B. And we know from the property of the cross product, we know that this moment needs to be perpendicular to RBA. And because RBA is coincident with x direction, it needs to be perpendicular to x in this case. And the moment also needs to be perpendicular to my force F. My force F has the same direction as y, so it also needs to be perpendicular to the y direction. So, a vector MB that needs to be perpendicular to both x and y, it means is a vector that needs to be at the same direction as z, right? Agree with me? So z is perpendicular to x and y, agree? That's why the moment needs to have the z direction. You get it? Understand or not? Oh, it comes from the property of cross product. I showed you last week, right? I showed you last week. And I show you in this example as well. Look at this. Look at this example here. Look, we did, look at this. Look, we did the cross product, right? Of the position vector with the force vector. So position vector is this one in green as component in the x direction only. And the force vector is this one in black only as a component in the y direction. Agree? So the result of this cross product is this vector that you have here in red. And you can see it only has a component in the z direction, right? So this confirms what I'm saying. Look, RBA is x component only. Force vector is a y component only vector. The result of the cross product is a z only component vector, right? This confirms. This comes from the property of cross product.
And could you say that it's simple? If you want to draw this vector, the third one, the answer, only would be because x-axis and y-axis are 0, so it only goes to z-axis.
Yeah, but no, but careful, because I can give you something like this. I can for example give you a 3D coordinate system, right? I can say this is x, y, z. Hold on, and then I can give you this force here. I can say this force is going to be a vector with a component in x direction, a component in the y direction, a component in the z direction, right? So if you want to calculate the moment about this point, let's say this point O, so this is point A where the force is applied, you need to define this position vector R, which is going to have a component in the x direction, y direction, z direction, right? Right? So now I ask you a question. What should be the direction of the moment produced by this force F? So we are going to do moment about O is going to be equal to this cross product, right? Agree with me? So what is going to be the direction of this MO, of this moment, this vector? Do you know? Can you tell me? You can't, right? So this is a very generic way where this position vector and force vector, they have a very general orientation in space, in a 3D space. So, but the good thing is that if you do this cross product, the direction of the moment will come out automatically from the cross product. You don't need to worry, right?
What I mean is for 2D.
For 2D, yeah, for 2D is always that. Okay, let's do another example 2D. Okay? So let's do something like this. We have a force like this, which is 1,000 newtons. Okay? And I will say, okay, this angle is of this force with the horizontal axis is 30 degrees. All right? So let's say, for example, this force is applied at this point, which is point A. And I want to calculate, for example, let's see, I want to calculate the moment about this point B. My question is, moment about point B. All right? So we need to define this vector, this position vector, RBA. And for that I'm going to say, so we need to have a, let's say for example, this angle here is 45 degrees, let's say, 45 degrees. And then I need a coordinate system. Let's say this is my x direction, this is my y direction. Okay? A generic problem in 2D, the force vector makes 30 degrees with the horizontal direction, for example. The position vector connecting point B with point A makes 45 degrees with the vertical direction, y. All right, so let's define. So I'm going to show you that the moment, the vector moment, is going to have only z component. All right? So let's do the cross product. So let's write first the position vector, RBA. So we need to do this cross product to obtain the moment, RBA, external with the force. So let's start with the position vector. What is the x component? Okay, in order to simplify, let me say the norm of RBA is equal to 10 meters, for example. All right? So my x component is going to be 10 cos or sine of 45 degrees, right? Same. You agree with me? The y component is going to be how much? Positive or negative? Why positive? Why? Look, if you decompose this vector in the y direction, you will end up with this component in the y direction, right? Which is opposite to your y-axis. So it needs to be negative, all right? Careful here. You tend to do a lot of mistakes in this kind of decomposition of vectors. So very careful, because one signal wrong, everything is wrong at the end. A bridge can come down. Trust me. All right? So you need to be very careful. So this needs to be minus 10 cosine of 45 degrees. Z component is 0. Agree with me? So everybody agrees this position vector, RBA? All right? Now, external product with my force vector. My force vector is 1,000 newtons. So what is the x component of my force vector? Cos 30, right? Times 1,000 newtons. Agree? So we have 1,000 cosine of 30 degrees. What is the y component? Sine of 30. Very good. Positive, right? So 1,000 sine of 30. What is the z component? 0 as well. Okay? So let's do now the cross product. So I'm going to do it here below. So if I do now the cross product, so let's start with my x component. I have what? This times 0, which is 0, minus 0 times 1,000 sine 30, which is also 0. So my x component is 0. Let's do now the y component. The y component, I need to do this cross product. This times this, minus this times this. 0 as well. Agree with me? Now, z component. This times this, minus this times this. This is not 0 now, right? So this will give me, at the end, this will give me 10,000 sine 45 sine 30 minus, with minus is plus, 10,000 cosine 45 cosine 30. As you can see, right? You can clearly see from here, right? The result for the moment is a vector again with component in the z direction. This is in two-dimensional problems only. You always have a moment with a component in the z direction only. If you are doing 3D problems, you will have a moment which will have a component in x, y, and z directions. But that will come out automatically from the cross product. So that's why I strongly recommend in 3D, always calculate the moment by doing this cross product. Always. In 2D, you can also do it, or you can do with the other method we discussed before. All right? Okay? Yes.
When you introduce the cross product, first you told us that the cross product of two vectors is the area of the hybridograph formed between the two.
Yeah.
Why is that? Why does it give the moment of the two vectors in each other? What's the link between the area and the moment?
No, the moment. Well, it's still the area, right? So let's see. If you have, for example, a position vector like this, RBA, and if you have a force vector like this, imagine this case where this angle is 90 degrees, okay? Let's make this for 90 degrees. It will work for the same. So if this is my force vector, look at this. When you do this cross product, RBA, cross product with F, when you do this, you will get the moment, right? But what I told you was the norm of this moment is equal to the norm of the position vector times the norm of the force times the sine of this angle alpha, right? Now, what you are saying is, if I move this force vector to here, a parallel is, so this is the same as this, I just move it here, and then if I calculate the area, I can delete this one now. So if I calculate the area, sorry. So this area, right? You agree with me? So when this angle is 90 degrees, in this example I said this angle is 90 degrees, right? So this area is going to be equal to what? RBA, which is this length, RBA, agree with me? Times this length, which is F. Right? And then I told you last week that the norm of the vector, which is the result of a cross product, that norm is equal to the area, to this area, right? Which confirms, look in this previous example we did. This previous example, we considered this angle 90 degrees. We obtained the norm of the moment equal to RBA times F. If you calculate the area of the parallelogram made by this RBA and F, that area is also equal to RBA times F. And that area, I told you, is the norm of the vector, which is the result of the cross product, in this case, the moment, right? So, you are absolutely right. So the area is equal to the norm or the intensity of my moment. Okay?
I think the question is, what's the definition of the moment?
Oh, the definition of the moment is position vector times a force, right? So the higher this length, the higher the moment you will get, or...
I think that from your definition, the moment is the force perpendicular to...
No, perpendicular. No. The force and the position vector, they can have any orientation in space. Look at this example. I gave you into D. I said position vector is a vector that makes 45 degrees with the vertical direction, right? Force makes 30 degrees. They are not perpendicular. The force and the position vector, they are not perpendicular in this example, right?
No, but I'm saying the moment is perpendicular to both.
No, this is just the moment is perpendicular to both, yes.
I'm saying, is that the definition of the moment? Because from A level...
No, definition of the moment is a position vector times a force. This is the definition.
I think that's all. From A level, we understand the moment as the resultant force acting on a point. But the definition here...
You said the result...
The resultant force acting on a point. That's why we're...
Resultant... No, that is not definition of a moment.
No, but I'm saying that's why we're a bit confused, because we would just add up the forces acting...
No, a moment is not a force. Right? What you are saying is a force. Resultant of a force acting on a point is still a force. It's not a moment. Right? Moment is when you multiply that force with a distance, then you get a moment.
I understand. I'm just saying the confusion comes because at A level, when we used to take moments, we used to understand that as being the resultant force.
Please, be quiet. No, if you learn that in A levels, is not correct. Right?
No,
that is not a moment.
I think your definition makes sense, and I think the problem is we now have two.
Okay, but anyway, so forget that. So you have a force is a force. A moment is a force times a length or a distance. Okay, right? For example, let me give you an example. A torque is also a moment, right? Imagine, for example, you have something like this. Okay, imagine your car. So you have the floor here, you have the wheels. Imagine this, all right? So what happens to your car? So you have the engine here somewhere inside, right? Is giving a torque to the wheels, right? Through the gearbox and all of that stuff. So what is happening is you are putting on the wheel, you are putting a torque like this. We call T, but this is in fact a moment. And why does your car move in this direction? Why does it go in this direction? Because the wheel is making a force on the ground, on the floor, in this direction, and the ground will react, this is Newton's third law, will react on the wheel with a force in the opposite direction. Right? So this force is because of friction between the tires and the floor. So this is Newton's third law. So how do we calculate this torque? So this torque, T, basically is going to be what? Is going to be, so imagine if the wheel has this radius R, is the radius of the wheel. This torque is going to be equal to the radius times the force, this force F. Right? This is the definition of a moment. Is a force times a length, in this case, is the radius of the wheel. And that will give you the torque that you need. So, if you need this force to move the car in the front with some velocity, with some speed, you know the radius of your wheel, so you know the torque that your engine needs to deliver to get the movement of your car, right? So this is the definition of a moment. In this case, it's a torque, which is the same thing as moment, right? It's not only a force, it's a force times a distance, a length. This is a moment. And when you do the cross product to obtain the moment, you always have a position vector with a force vector. That will give you a moment. Right? So I hope that you are not so confused now. I don't know. But anyway, we will do more examples. All right, so let's move on. So let's see what time is it. Let me just introduce a very important concept now. So this is very important what I'm going to do now. So imagine you have something like this. You have a force F applied at this point A. All right? And imagine that you have now a force which I'm going to say is equal to minus F applied at a different point B. So these two forces, F and minus F, they have the same intensity, same norm, or the length of these vectors are the same, but they are opposite, right? So if I calculate the resultants of these forces, which is summation of all the forces, this resultant is going to be equal to 0, because they are symmetrical forces, they have the same norm, so they cancel each other, right? So we call this system of these two forces in these conditions, we call this a couple. All right? If you have two forces that are opposite, they have the same norm, but they are opposite, so that they cancel each other. These two forces, they form what we call a couple. Not difficult to memorize this, I think. So what I'm going to do now is I am going to calculate the moment produced by this couple, or by these two forces, about, for example, this point O. Okay? And in order to do that, I need, of course, to define my position vectors, right? I need to define this position vector connecting point O to point A. I will call it ROA. And I need to define this position vector connecting point O with point B. I will call it ROB. Okay? Everybody's following? So we have a couple, these two symmetric forces, and I'm going now to calculate the moment produced by this couple about point O, and that moment, MO, is equal to what? Is equal to the cross product of my position vector ROA with my force F plus the moment produced my position vector ROB times my force, which is minus F. You all agree with me? So, I have two forces here, F and minus F. I want to calculate the moment about point O. I just need to add the contribution of my force F to the moment plus the contribution of my force minus F to the moment, right? And now I can work this a little bit. I can say that I will have ROA minus ROB. So I'm sending this minus signal to the position vector. I can do that. And then I multiply this by F. Okay? And now, this ROA minus ROB, this term here, I'm going to say this is equal to my R vector, which is, or if you want, I can say this is going to be equal to RBA, which is a vector connecting point B with point A. So I am subtracting two vectors, and the result of that subtraction is this vector that you have here in red, RBA, connecting point B with point A. And then I can say that this is going to be equal to RBA, external product or cross product with my force F. Right? And one important conclusion is, just a moment. One important conclusion is the result of the moment produced by this couple of these two forces, F and minus F, is going to be this cross product of a vector that only depends on the position between point B and point A. So basically what I'm saying is that we evaluated the moment about point O, but the position vector starting on point O does not appear there anymore. Right? So, yeah, someone was asking something. Question here, right? Yes.
See that F, is that the resultant force?
Sorry?
See that F?
F is the force.
Is the resultant force of F and F minus F?
Yeah, it's the same. Yeah, look from this equation. What we did was we sent this minus signal that you see here, we sent it here to the position vector, and then we said this is the distributive property, right? And then we just, if you multiply now ROA with F, you get this term. And then if you multiply ROB with F, you get this other term here, right? Okay, look at this now. Look what I'm going to do now. Imagine I want now to calculate the moment about this point. Point C. A different point. I want to calculate now the moment produced by this couple about point C. So what do I have to do? Well, I have to connect point C with point A with this position vector. I will call it RCA. And I have to connect point B with point C, and I will call this position vector RCB. All right? And then, if I want to calculate the moment about point C, I will have to do it in a similar way. So I will have my position vector RCA, external with my force F, plus my position vector RCB, external with my force minus F. That will be equal to RCA minus RCB, external with my force F. And my conclusion is this is going to be again equal to RBA, external F. Which is an amazing result, right? Look at this. It doesn't matter, basically. So we obtained the same result as when we calculated the moment about point O. So it means what? It means it doesn't matter which point I choose to evaluate the moment produced by this couple. That moment will always depend on the position vector connecting the 2 points A and B where the forces are applied, cross product with my force vector F in the couple, right? This is a very important property of this couple. So it doesn't matter which point we choose to calculate the moment, we can always obtain the same result for the moment produced for the couple, which is RBA cross product with F. Right? So we are going to see on the second half of the lecture how we can use this very important property to solve our equilibrium of 3D rigid bodies. Without this, we cannot do it. All right? So we'll see that in the second half. Let's do a break now. 5 minutes maximum. We are a bit late. All right? That. So you did ask me some questions regarding. So one that was asked us just right now was, why did we get RBA and not RAB? So in this previous slide, we obtained here RBA. So why is it RBA? So basically a position vector starting at point B and going all the way to point A, and not the other way around. The reason is, and I'm going to do it here, you get this vector which is ROB connecting point O with point B, and you have this vector which is ROA. And then what we want to do is we want to do ROA minus ROB. Correct? And I can write this in a... So this is a subtraction of two vectors. I can write this as an addition of these two vectors. How? I can say this is equal to ROA plus minus ROB. You all agree? And what I'm doing basically, so let me try to move this a little bit more here. So what I'm doing basically is, if I use this vector, this is my minus ROB. Agree with me? You all agree with me? So if I add these two vectors now, I need to draw parallel lines to these two vectors, and then this is going to be the result of my addition. So this is going to be RBA, which is equal to ROA plus minus ROB. Right? So this RBA that you have here in red is in fact, don't forget this is my point B, is in fact, this is my point B here, right? Is in fact a vector starting at point B and going to point A, right? Not the other way around. So that was one first question that you asked me during the break. The second question was, again, something regarding the moment. I was given this situation here in a 2D problem. If we have a position vector like this, if we have a force vector like this, the question was, we learned in A levels that we obtained a moment which basically is an anti-clockwise rotation. And if you think carefully what you are saying here, this anti-clockwise rotation, if you think this rotation is going to be about an axis which has the direction of my z-axis, right? It's going to be a rotation about z-axis. Agree with me? So, if you use your right hand and if you align this with the position vector, so let me try to do it here graphically. So you have the position vector and you have the force vector here, right? So when you calculate the moment, if you do so, let me see if I can draw the. If you align your fingers, your right hand, if you align your fingers with your position vector like this, and then if you try to rotate your fingers from R towards F vector, you rotate like this, right? So your thumb will give you the direction of your moment. Look at this. If my fingers are aligned with R, if I rotate now my fingers through F direction, like this, anti-clockwise in this case, my thumb will tell me my moment is in the Z direction, right? It's a rotation about an axis on the Z direction, right? Yeah?
This seems similar to the right-hand grip rule.
Yeah, that's it. Yeah, that's what I'm saying. Thank you for the English correction. That's exactly what I'm saying. Right hand rule. That's what I'm saying. So, right hand rule is you use your right hand, you align your fingers with the position vector, you rotate your fingers towards F, and then your thumb will tell you the direction of the moment. Z, right? So, that's how it works. Now, let's continue with... maybe I can use... Yeah?
Isn't the moment supposed to be anti-clockwise or clockwise?
There is a convention for the moments. I use the one that says if your moment rotates anti-clockwise, I assume positive moments. If they rotate clockwise, is negative moments. Right? But we will see many examples, all right? Don't worry with that. All right, so let's go back to this couple, the moment produced by a couple. So the conclusion is the moment produced by a couple is equal to the position vector connecting the two application points of the forces, cross product with the force. And this is we call this a free vector because this moment produced by a couple does not depend of point O, of point C, of point D, E, F, it doesn't matter. Is a moment is equal everywhere. Right? It's a free vector.
You just said that anti-clock is the negative moment?
Positive.
Positive. The clock one is
Yeah.
negative moment.
Yeah.
So what does it mean negative moment?
Okay. So let me give you an example here. Imagine this situation here. You have your X and Y axis. And then imagine you have this. So X, Y, your Z is, if you apply the right hand rule, if you rotate X towards Y, your Z is outside of the whiteboard, right? So if you have a force here, like this one, and if this is your position vector, r, the moment you will obtain will rotate like this, right? Anti-clockwise. Right? And if you rotate like this anti-clockwise, you will have a vector in the z direction which has the same direction as the positive z. Isn't it? Don't you agree? Look, if you pull with this force, it will rotate about a z-axis, anti-clockwise, right? So if you rotate anti-clockwise around your z-axis, you will move on the positive z direction. Isn't it? Isn't it? Look, haven't you guys never opened a bottle of wine? Okay, if you know the cork opener, right? If you rotate clockwise, the cork opener is going down, right? Into the cork, right? You are rotating clockwise, so you are going down, right? You can rotate clockwise. So when you rotate anti-clockwise, the cork opener is coming up, isn't it? So imagine you have a z-axis aligned with the cork. Positive z is on the upward direction. If you rotate anti-clockwise, you are coming on the positive z direction, right? So that's why I say when we have a moment anti-clockwise, and if that anti-clockwise rotation is the same direction as the z-axis, we use it as positive. Now suppose I have this situation now that my force is applied on this direction. Right? What happens here? What happens here is that my moment will now be a clockwise moment, right? Agree with me? So this moment will rotate in a clockwise direction, so I'm going to the negative z-axis. That's why you get a negative moment at the end. But the good thing is that's why I recommend you guys to always use the cross product. Because if you do this cross product, we can do it very quickly here. You get the moment is going to be equal to this, right? This cross product. The position vector is in the x direction. The force vector is minus f. In this case, agree with me? So if you do this external product, you get what? You get a vector in the z direction that is equal to minus rf. Here it is. Clockwise, negative moment in the z direction. So if you do the cross product, even in a 2D problem, you always get the result correct, automatically. You don't need to worry if it is clockwise, anti-clockwise. It comes out automatically. So I strongly recommend, it's not difficult, you just need to memorize this cross product rule. You put that in your head, then your life will be very easy. Okay? So I need to start now talking about, otherwise we don't have time, a very important issue now. So I'm going to do the following. Imagine you have a 3D structure, a very generic structure. I represented the structure like that. And then imagine I have this point here. Let's say this is my point A. And at this point A, I have this force F applied at point A in my structure. Now imagine that I have here another point B, and I have this force P, for example, applied at point B. And I have a point C here with a force T, and so on. Imagine I have many different forces applied at different points of my structure. So I cannot just come here and say, well, my equilibrium equations is summation of forces equal to 0. Well, we will need this to study the equilibrium, but it's not enough. The reason is because all these forces, they are applied at different points. Not in a single point like we did last week for the equilibrium of a particle. So I need to have something more to study the equilibrium of 3D rigid bodies. And what I'm going to do is I'm going to start. So I'm going to delete this now, and I'm going to start with a very important procedure, which is I want to get an equivalent system to this one. So we have now distributive body with a force F applied at point A, and I want to get an equivalent system at point B where basically I want to replace that force in point A and move it to point B, but I want to maintain the equilibrium of the structure. I cannot destroy it. So how do I do that? So what I'm going to do is something like this. I'm going to include in point B a force F, the same force that I have in point A. I'm just going to copy that force to point B. But if I do only this, I am altering the equilibrium. I'm changing the equilibrium, right? This is not the same as the initial configuration with a force only at point A. This is completely different. So how do I make this the same? Well, I make this the same if I include a symmetric force here at point B minus F. Don't you agree? So if I add at point B a force F and a force minus F, they cancel each other, then I get exactly the same initial problem. But now you might be asked, why did you do all of that? It seems your system is much more complicated. You didn't simplify anything. Not yet, because if you look at this force F at point A and this force minus F at point B, they form what? A couple. Exactly. So we are going to focus on this couple now. What did I tell you about the couple? Summation of forces produced by a couple is equal to 0. So what I'm saying is that this force F at point A and this force minus F at point B, they will cancel each other, right? In terms of forces. But a couple introduces a moment. And how much is that moment? That moment is equal to the cross product of this position vector connecting point B with point A. So that the moment produced by that couple, I'm going to say M is equal to the position vector RBA external product with my force vector. This is exactly what we obtained in this slide here when we calculated the moment produced by a couple. Position vector connecting the two application points of the forces of the couple, cross product with force. Right? So, this is a very, very important result. Why? Because now I can say, so I can replace this couple, this F force and this minus F force, I can replace this couple with the moment M. I can do something like this. Look at this. I can remove this force F at point A. I can remove the force minus F at point B. And the only thing I need to do now is I need to include the moment produced by the couple, and that moment M is equal to RBA cross product with my force F. And then look what I have. So I'm going to write on the right hand side here, I'm going to try to draw the initial configuration we had before. So before we had at point A, we had this force F at point A. And then I can say that these two systems, they are equivalent. So having our original system, this one here on the right, with a force only, a force F at point A, is equivalent to this system on the left with a force F at point B and a couple M, which is equal to RBA to F. So what I did, if you look carefully, what I did it was I transferred this force from point A to point B. But when I do this, when I transfer the force from point A to point B, I need to add the couple, the moment produced by the couple, right? M, this M. So at the end I will have an equivalent system, force plus a moment produced by a couple, right? And why is this important? Because, look now, imagine I have now a point C here with a force P. I can put in a different color with a force P. Imagine I have this my initial system. So point A and point C. I have a force F at point A, a force P at point C. So we transferred already on left hand side. We transferred already the force from point A to point B, and we added a moment as well. I'm going to do the same for this force at point C. Force P. So what I'm going to do is I'm going to include a force P here. So this is my P. It's the same force as I have at point C, but I need to add a couple. I'm going to put it now in green. And this couple, M in green, is going to be equal to my position vector connecting point B and C. Let me zoom in a little bit. Position vector connecting point B and C. External product with my force P. Right? Of course, I can now add these moments, this green, the moment in green and the moment in red. I can add them together to have only one vector, total moment. I can do the same for the forces. I can add my force F and P and have a resultant force. And I can continue. If I have another force in a different point, I can also transfer everything to point B by adding the force plus a moment. Right? Why is this important? Because now, look what is going to happen now. I'm going to copy this guy. Copy. Paste here. Yeah. So what I'm going to say is that I'm going to, in this point B, I'm going to have a resultant of the forces. So this resultant of the forces, as you know, we talk about the resultant is summation of all the forces we have in the body, right? This is the resultant of the forces, and I'm going to put it here in red. I'm going to have as well, I'm going to say MR, a vector, which is a moment. So this MR is going to be as well a summation of all the moments. I can say RI cross product with FI. A summation of all the moments. In this case, it was going to be equal to the summation of the moment we have in green with the moment we have in red. So I add all these vectors together and I have a resultant for the moments as well. And then I will have this equivalent system at the right hand side. This equivalent system here. And then you can see we have everything, forces and moments. On the right hand side here, we have everything concentrated in one single point of our structure. And what are we going to do now to study the equilibrium? Well, I'm going to say the resultant of the forces, they need to be equal to 0 to be in equilibrium. So in a 3D problem, we have three equations. Summation of forces in x equal to 0. Summation of forces in y equal to 0. Summation of forces in z equal to 0. Three equilibrium equations. And I'm going to say the resultant of my moments also need to be equal to 0 to be in equilibrium. Right? Resultant of the moments also need to be equal to 0 to be in equilibrium. And then we will have three additional equilibrium equations. X component of the moments equal to 0. Y components of the moment equal to 0. Z components of the moment equal to 0. Just a moment. So what I'm saying is that we will have something like this. Resultant of the forces. We are going to have X components, Y components, Z components. They all need to be equal to 0. The resultant moment, at that point, we will have a component in the x direction, a component in the y direction, and a component in the z direction. They will all have to be equal to 0 as well. Yeah.
Why should the motion be 0?
It's the equilibrium equation for the moment. So when we studied the particles, we said summation of forces need to be equal to 0. The balance of the forces, right? I also give you an example, right? You see, we have to do the same for the moments. The moments, they need also to be balanced. All the moments you have in that point, they need to be in equilibrium, balance. So that means equal to 0. Okay?
Yeah.
So this is the equilibrium equations you have for a statics problem. So we are going to work, do many examples now, and we have a lecture in the afternoon, right? We are going to do some examples, application of this. But what I want to emphasize is this procedure that we did. I'm going to summarize again because this is extremely important. So the situation is we will have a complex structure where we will have a complex geometry and we have many forces applied at many different points. How do we study the equilibrium of that structure? Well, before we start writing the equilibrium equations, we need to build an equivalent system force-moment. How do we do that? Well, we take advantage of the moment produced by a couple. The moment produced by a couple allows me to transfer a force from one point to another by adding a moment, the moment produced by the couple. So I can do that for as many forces I have in my structure. So at the end, I will have everything concentrated in one single point of my structure. This point can be any point you want, you choose for convenience. Of course, we are going to do many examples where I ask you explicitly, construct the equivalent system force moment in point A or in point O. I will ask you to do that. But when you are solving an equilibrium problem, this point B that we have here in the slide can be any point of your structure. What it means is that you need to concentrate everything in that point. The resultant of the forces and the resultant of the moments. Once you have everything concentrated in that point, then you can say, if this point is in equilibrium, or if these two vectors, resultant of forces and resultant of the moments, if they are equal to 0, then it means my entire structure is going to be in equilibrium, not only this point. That's the big advantage of this, because we built an equivalent system concentrated in one point. So basically, I transformed the equilibrium of a 3D rigid body into an equilibrium of one point. Of course, we have the moment there, but that is the big advantage of this procedure, okay? So let's do one quick example just to show you how this can be done. So I'm going to stop this one and start a new one. So in this example, you have this structure or this column here. You have basically three force vectors applied at three different points. Right? You have this 300 newtons here. These 300 newtons horizontal force applied at this point. You have this 500 newtons, this force in this cable that is applied in that point there. And you have another force here. So you have a 3D rigid body with 3 different forces applied at 3 different points. The question is, I want you to build the equivalent system, force, and couple moment, or moment, force moment, at point A, in this case, right? At point A. Right? So this is an example I took from the Ibler book, is this book here, which is the book we recommend for this model. Ibler is the name of the author. The title of the book is Engineering Mechanics Statics. You have many copies of this on the library. We follow this book, but you have also many different books in library, so you can just go there and grab some books and do some examples if you want. Okay? All right, so let's do this. So we need to build what? We need to build at point A. So basically what I'm saying is you need to have a resultant of the forces, R, and you need to have a resultant of the moments, MR. Okay? So let's start with the resultant of the forces. Let's do it here. So, resultant I just need to add all my force vectors that I have, right? So let's start with this one. Of course, we need to have a coordinate system. Let's say I will consider this to be my x-axis and this to be my y-axis. Okay? Z is perpendicular to these two. So this 300 newtons here, it only has a component in the horizontal direction, so I can say this is equal to minus 300, 0, 0. This force vector is this one, plus, I'm going to continue here below. Now let's do, for example, this one, this 500 newtons. You tell me how much is the horizontal component of this one? Minus 500 cos 30, is it? The vertical component in the y direction? 500 sine 30. Z component is 0, right? And now the last one is this. You tell me horizontal component 250 4/5 times 4/5. Is it? Is the sine of that angle, right? Is 4/5. Vertical component. How much is it? It's positive or negative? Negative. 250 times what? 3/5. Z component is 0. So it means we will have this resultant vector is going to be equal to, can you please do this? So you have minus 300 minus 500 cosine of 30 plus 250 4/5. How much is this, please? Can someone do the calculations for me?
Minus 533.
Minus 533. So I'm going to just replace that one here. Minus 533. That's it. Now the y component is 500 sine of 30 minus 250 times 3/5. How much is this, please?
100.
Huh?
100.
100?
Yes.
Okay. It's positive, right? 100. Z component is 0. So this is our resultant of the forces. Let me just... Okay? You all agree with this? Now, for the moments, let me try to move this. Okay. Now, for the moments, we will have basically to calculate the moments about point A. Okay, we will, of course, we need to construct this couple. So let's do the couple one time and then we will do it in a quicker way. So let's do, for example, for this 300 newtons. So let's start with this one first, this 300 newtons. So let's build a couple for this 300 newtons. So in order to build a couple, what I'm going to do is I'm going to add, so let me zoom in. I'm going to add this 300 newtons here. And then, of course, I need to add this minus 300 newtons in this direction, right? So where is my couple? My couple is this with this, right? And how much is that moment? So what is my position vector that I need? I need position vector connecting point A with this point here. I need this position vector in blue. Let's say this is my R1 position vector. I can say this R1. What is the X component of this position vector? 0. What is the Y component? 1 meter. Z component, 0. And in order to have the moment produced by this couple, I need now to do the cross product of this with this force vector here, 300 newtons. What is the X component of this 300 newtons? X component, how much is it? Plus or minus? Minus. Y is 0, Z is 0. So this is the moment produced by these 300 newtons about point A. Let's see. Now, for the other forces, we can do a bit quicker. So I need to add now the moment produced by this force. Let's focus on this one now. So I need to add here. I need to include first the position vector. So starting at point A and going all the way until this point. This is my position vector. R2, let's say like this. I need to define this position vector. What is the X component? 0. What is the Y component? 2. What is the Z component? 0. Now I need to define this force vector here. X component. Minus 500 cos 30. Agree? Y component. 500 sine 30. Very good. Z component 0. So the moment produced by that force about point A is the result of this cross product. That is done as well. So the last one we have to do is this force. Now this one. Okay. So I need to add now. So my position vector, what is my position vector? My position vector is this one. Oops. Let me try to do it. This. Wow. What's going on? This one here. So this is my R3. Yes?
The 500 newton force, do not take into account 0.2 meters.
Oh, you're right. Very good. I didn't see that. Sorry. So before we do this, so it is this. The force is fine. The position vector is not 100% correct, right? So we need to fix this guy here. So the position vector is this one from here to here, right? Our R2. So let's say it is. You tell me then x component minus 0.2. Y component 2 meters. That is same, right? This is correct. Yeah, that's good. Thank you. Very good. Now, let's go back to our position vector, which needs to be this one, our R3, for this force. We are doing this 250 newtons now. The moment produced by this 250 newtons about point A. So position vector first, you tell me x coordinate 0.5, y coordinate 3, z is 0. External product with the force vector, you tell me x. I think force vector we did already, right? Is this one, right? You all agree with me, this is my force vector, so I can just copy this one, right? I can say it's 250, 4 over 5, minus 250, 3 over 5, 0. So if you do, so you have here this cross product you need to do, another cross product you need to do, another cross product you need to do. The good news is that it will have only component in the z direction. You can confirm that at home when you do these cross products, these calculations. And then this z component, this one here, this one here, you need to calculate at home. We don't have time for this. We can do this one eventually, which is very easy. This first one is 300, right? This second one, if you want, I can put this way. I can just write so minus 100 sine 30 plus 1000 cosine 30, and this one 0, 0, you will have minus 125 3 over 5 minus 750 4 over 5, right? So if I didn't have any mistake doing these multiplications, that's what you have. You just need not to add all of this together, and then you will obtain this z component here for the. Don't forget, this is our. This is going to be equal to my bending. My resultant moment. So what is going to happen is, at the end, let me try to copy this, paste. So at the end, what you are going to have is, you are going to have an equivalent system right? So this is your point A. So you will have this equivalent system where the only forces and moments you will have is you will have a resultant of the forces which is given by this vector here. Don't forget, this is our resultant of the forces, minus 533 100. I can copy You will have this for the summation of the forces, and you will have a resultant for the moment, which is going to be 0, 0, and the z component is equal to, maybe I can copy this over there. Is going to be equal to 300. Minus 100 sine of 30. Plus 1000 cosine of 30. Minus 125, 3 over 2. Sorry, I don't have space there. I need, so minus 125, 3 over 5, minus 750, 4 over 5. So this is going to be my MR vector. Okay? And then now I can clean this a little bit more. That's it. That's what I want to show you. Oh. So I need to so you will have, okay, you will have, now you can see, you will have an equivalent system in our structure, same structure, but as you can see, everything now is concentrated at point A. You have resultant of the forces, this R vector, minus 533, 100, 0, which is the summation of all the forces. And you have then the resultant of the moments, which is this vector in red, which is given by this vector you have here with component in z direction only. Right? So you can compare the two systems. The first one, this, where you have everything, three forces applied at three different points, and you can compare with this one where you have everything, the resultant of the forces and the resultant of the moments, applied at one particular point, point A. Right? This is very critical. In the afternoon, we are going to do a more elaborated example using this, okay? Let's start. Good afternoon. Is this working? So let's do this example today in the afternoon. We have only 1 hour. So everything we have been doing so far is just to build the equivalent system force moment at a point. We are not writing the equilibrium equations yet, right? So at this moment, the only thing we are trying to get is to replace the original system with forces applied at different points. Like you can see here in this example, you have a force F1 applied at point A and a force F2 applied at point B. So we want in this example to replace this system with an equivalent system with a force and a moment applied at point O. So the first thing I'm going to do is to obtain the resultant of the forces. Basically what I have to do is I have to In this case, I have two forces, so that resultant is going to be equal to force F1 plus force F2. I have the vectors of these two forces. So I can continue here. Force F1. The x component is this one, 10. Agree with me? So I will have 10 in the x direction. The y component is this minus 15. So I will have here minus 15 in the y direction. And the z component is this minus 40. You can see here, we talked about this last week. You can see minus 40 is multiplying a unit vector, k, which has a norm 1 and gives me the direction of my z-axis. We talked about this last week. I uploaded today in Blackboard some notes on vectors and tensors, where all of this is detailed there. You can go and check. So the z component is minus 40. And this is my force vector F1. Right? I need now to add my force vector F2. My x component of this F2 is minus 15. My y component is minus 20, this one, right? Is the component that is multiplying the j unit vector that gives me the direction of my y-axis. So minus 20. And my z component is minus 30, right? Is this one? Minus 30. And that will give me my vector F2. You see? And now, the only thing I have to do, I just need to add these components. So starting with the x component, I have 10 minus 15 is minus 5. Looks basic, but you have many mistakes in these kind of things, right? So we have to do it very slowly so that you are following. So minus 35, minus 70, right? This is my resultant of my forces, R. As you said, it's not difficult at all, right? Now, let's calculate the moments now. Let's calculate we need now to get the moment produced by these two forces about point O. Okay? So let's start with the moment produced by force F1. So we need to define a position vector connecting point O with point A. So we need to have this position vector starting at O and going all the way to our point A. So this position vector, I will call it ROA. And that's what I need to define now here for the cross product. To obtain the moment, I need to do the cross product with the position vector with the force. So you tell me, what is the x component of this position vector, ROA? You think it's 0? You all agree 0? Yeah, it looks like a 0. What about the y component? How much is it? Y 100. The y component is 100, are you sure? It's 250, right? So I want this I want this component here. I'm going to look. This component here is my y component, right? This is equal to this 250. You agree with me?
Yes.
So 250 here. What about the z component? Z component, I'm looking for this one. What is this component here, right? Is my z component. You all agree? How much is it? 100. Now I need to do the cross product with the force vector F1. And force vector F1, we have it already here. Is this one here, right? So I can just copy is 10 minus 15 minus 40. Okay? So I can write like this. This is my position vector, ROA. And this one is my force vector, F1. But that is only the contribution from force F1. I need to add now the contribution from my force F2 for the moment. So for the force F2, I need now to get the position vector connecting point O with point B. It's always a good idea to draw these position vectors because you need to get the components of these vectors. Right? So this is going to be my position vector ROB. I need to get the x, y, and z component of this vector. You tell me the x component. How much is it? 150. Good. Y component? 25. It's not 0. Look, you have here this 25, right? That will add a component in the y direction, right? You agree with me or not? So it's 25, right? 25. And the z component is 40. Very good. Right? And now I need to do the external with my force vector, which is this one here. My F2 is this one. We are already. So I'm just going to add it here. Minus 15, minus 20, minus 30. So this is my ROB. And this one is my F2. Right? You all agree with this? So the only thing I have to do now is the cross products, and then I get the moment. So let's do these ones. So I'm going to do it here. So I'm going to continue here, okay? So MO. So let's start with the first cross product, this one here. So my x component is this times this minus this times this. So it's going to be minus 250 times 40. Minus with minus is plus 100 times 15. Let me write this. This is 250, right? Y component is, the y component is this cross product. This times this minus this times this is my y component. So it's going to be 1000 minus 0 is 1000. Okay? And the z component is this times this minus this times this. We are always doing the cross product. That's why we call this cross products, okay? So it's 0 minus is minus 2500. So this is the result of the first cross product. Now we need to do the second cross product. Is minus 2000. You are saying this last one? Yeah, is this times this minus this times this? Oh, for y. So let's see the y. You are saying 1000 here. Okay. So you have to do this cross product. This times this minus this. In the y direction, you change the signal. Right? That's why. I had some questions in the morning. If you can do the cross product in a different way, like doing the determinant of a matrix, you can do it. It's up to you. What I want is just the cross product properly done. It doesn't matter if it is like this, like we are doing here, or if you have a different technique to get the external cross product. It's perfectly fine. You know what I mean? So just get that right. Now let's do the second one. The second cross product. Then we need to add. So x component is this times this minus this times this one. Okay? So that will be minus 25 times 30. Minus with minus is plus 20 times 40. This is the x component. The y component, you need to do this cross product. So you will obtain minus 40 times 15. Minus with minus is plus 150 times 30. And for the z component is this times this minus this product here, this cross product. So you get minus 150 times 20. Then minus with minus is plus 25 times 15. That's it. Okay? And then if you do these calculations, you will obtain the... So if you now just add these components, you will obtain the total moment, right? Okay, so... And then, at the end, this means what? This means... This means at the end that you basically will replace this system. So basically you will build an equivalent system where you don't have this force, right? Applied at these 2 points. But instead of that, you will have what? You will have a resultant of the forces at point O, which is the summation of forces at that point. All those... Basically, this is F1 plus F2, like we did before. And then you will have a moment at point O, which is the moment produced by F1 and F2. So this system, with only a force and a moment at point O, is equivalent to the initial system with a force F1, F2 applied at point A and B. Right? And the value of this resultant force, you have it here. This resultant force is this vector. And the moment you have at point O is the result of these calculations that you can easily now finalize at home. Okay? let me copy this. So let's take this same example. Let's take this same example and let's modify it a little bit now. And what I'm going to say is something like this. Imagine that I now have for example, I'm going to add here two more forces. I'm going to have, at this point here, I'm going to add this force. I'm going to say this force is force P, which is given by, I can try to put in the same format, Px I plus Py j plus Pz k. So imagine that I modify this problem a little bit and then I say, okay, I have this force P, which I don't know what are the components Px, Py, and Pz. And let me choose a different point. For example, imagine that I also include, we don't have too many points here, but let's say, imagine I also include oh, that's fine. I can use point O. Imagine I include now here at point O another force, let's say it's T, where I have this Tx in the x direction, Ty in the j direction or y direction, and, oh, I did something. Yeah. And Tz, which is the component in the z direction, okay? So why am I doing this? Because in the previous example, as you can see, for example, for the resultant of the forces, we calculated at point O, this vector here, you can see from this example that this resultant is not equal to 0, right? You have x component of minus 5, y component of minus 35, z component of minus 70. Same thing for the moment about point O. You will have a component here. You will have a component in the x direction. You will have a component in the y direction. And you will have a component in the z direction. And they will not be 0. So this means what? The system is not in equilibrium. Right? Because the summation of forces is not 0. The summation of moments about point O, in this case, is not 0. So this system, under the action of these two forces, F1 and F2, is not in equilibrium. What I'm doing now, by changing this problem, is I'm including two extra forces at different points. And I don't know the value of these forces. Right? I said force P as component Px, Py, Pz, which I don't know how much it is, these components. And I also had a force T with components Tx, Ty, Tz, which I don't know the value of these components as well. And I'm adding these forces so that I can restore the equilibrium of the system. So at the end, we need to have resultant of the forces equal to 0, resultant of the moments or summation of the moments equal to 0 as well. And from these equations, you can see that we will obtain 6 equations. So 3 for the forces, 3 for the moments, makes 6 equations. And from these 6 equations, we will be able to calculate these 6 unknowns, which are Px, Py, Pz, Tx, Ty, Tz. We will have a system of 6 equations for 6 unknowns. So let's do that. So what do we have to do for this modified problem? We have now to, let's use the same point O to get our moment and the resultant of the forces. So for the case of the resultant, I'm just going to copy this. So let me see if I select this, copy, and then I can paste it here. Okay. So this is the previous resultant that we had. Now I'm going to add so I'm going to say now that my resultant is going to be equal to this plus, now I need to add what? I need to add the x component of my force P, which is Px, plus the x component of my force T, which is Tx, right? Same thing for the y direction. I need to add the y component of my force P and the y component of my force T. Same thing for the z direction. I need to add the z component and the z component of force T. Then my resultant at the end is going to be equal to -5 plus Px plus Tx minus 35 plus Py plus Ty minus 70 plus Pz plus Tz. Okay? So the resultant of the forces, we have it. Now we need to calculate the moment. So I'm going to copy from the previous slide. I'm going to copy this term here, copy, paste. Let's see. Yeah. So this is the moment that we obtained before. Now I just need to add the moment produced by force P and force T. So I need to add here, so plus, I'm going to continue. So these two terms that you have here, this one and this one, are the moments produced by force F1 and force F2, right? We did before. Now I'm just adding the moment produced by force T. Let's start with force T. What is the moment produced by force T about point O? You tell me. Don't forget definition of moment is cross product of a position vector with a force vector, right? So my first question is, where is my position vector for force T? Is 0, right? My force T is, the application point of force T is point O. If I'm calculating the moment about point O, it means the position vector is 0. So it means the moment produced by force T about point O is going to be 0. We don't need to include it. What about the moment produced by force P? Is it going to be 0? No. Our position vector in that case is going to be this one, right? This one I'm including here in red. And then we need to include this. So it will only have a component in the z direction equal to 100. You all agree with me? So we can say that we will have 0, 0, 100. External product with my force P. And my force P is what? Px, Py, Pz. Right? This is my force P. Look at this. My force P is Px, Py, Pz. So summary is, so I can do it very quickly because I can copy here. So let's see. I can copy this bit and paste. And then I can now add, so plus plus. So let's see. In the x direction, we have minus 100 py. In the y direction, we have 100 px. I'm doing the cross product, okay? In the z direction, we have 0. All right? So, we have I'm going to copy the resultant of the forces. I did something wrong. Copy. I'm going to use a new slide. I'm going to paste it here. So this is the resultant of the forces. I'm going now to copy the moment. So I'm going to select this. Copy, and I'm going to paste it here. So this is my moment about point O. I'm going to write it like this. MO is equal to this. And now what I'm going to say is that the resultant of the forces is going to be equal to 0, to be in equilibrium. And the resultant of the moment at about point O also needs to be equal to 0 to be in equilibrium. I think in this one I can probably do here. Yes, it's better to do it here. Needs to be equal to 0 to be in equilibrium. And then what is going to happen is, look at this. First equilibrium equation, summation of forces in the x direction equal to 0 is this equation you have. Second equilibrium equation is summation of forces in the y direction equal to 0. Second equilibrium equation. Third equilibrium equation is summation of forces in the z direction equal to 0. Here you have your third equilibrium equation. Fourth equilibrium equation is summation of the x components of the moments equal to 0. So you will have, this is going to be our fourth equilibrium equation. Summation of the y components of the moment equal to 0. That will give you your fifth equilibrium equation. And your last and sixth equilibrium equation is the summation of the z components of the moment equal to 0. And then what you have here, you will have a system of equations with 6 equations for 6 unknowns, which are px, py, pz, tx, ty, tz. And if you calculate these components, which are the components of the force P and T, then you know which forces, and you know everything about this force. You know the norm of these forces, because you can then calculate the norm. You know the direction of these vectors, because you have the components of the vectors, right? And then you can say that you just found, from the using of the equilibrium equations, you just found these two force vectors, P and T, that you need to use so that the entire system is in equilibrium. Yes?
Why don't we have any moments from T?
Why don't we have any moments produced by T? Okay, we can, I can explain here in this drawing here. So let's focus on the moment produced by this force T about point O, right? We need to have a position vector, right? Connecting point O with the point, or with the application point of the force T. What is the application point of force T? force T is applied at point O, right? So that position vector is a null vector. So the moment produced by T about point O needs to be equal to a position vector connecting, in this case, point O with point O, which is 0, times force T. That will give you the moment, right? Because the position vector is 0, right? It means the moment produced by T about point O is going to be 0. And don't forget, we are building the equivalent system at point O. We are calculating the resultant of the forces at point O and the moment about point O. So we are replacing the system with an equivalent system where everything is concentrated at point O. And then after having that, what we say is that the resultant of the force is equal to 0, and summation of the moments about point O equal to 0. And then this is our equilibrium equations now. And we can find the unknowns, P and T. Yes?
Shouldn't the moments that F1 and F2, shouldn't the Z component be equal to that? Because the third one is 0. Because the second one there does from minus 2,625 or something.
Okay, you are saying this one, right? The moment produced by F1 and F2 about point O. So let's review this moment. So
It adds up altogether to minus 5,000 and something instead of
yeah, well, I might have had some mistake, but let's check, okay? So let's see, starting with F1. So the position vector is this one. You all agree with me, right? So this position vector, so let's review what we have. We have 0 in the x direction, which seems correct to me. We have 250 in the y direction, which is correct. Is this 250? And we have 100 in the z, which is this 100. It's correct. Position vector is correct.
You mean when you added the two extra forces for the resultant moments and the Z component at the end?
Oh, you are saying this one here.
You've got
This one, we get 0 here.
yeah.
Oh, why we get, okay.
The other side you've got equal to 0.
Okay, let's see why. So I think we need to go to this slide, right? We did it here, right? Is this cross product here, you're saying? Yeah, because look, when you do the Z component, you need to do this cross product. This 0 times Pi minus 0 times Px. So it means the result is 0 at the end.
The left-hand side is not 0.
The left-hand side is not 0. What left-hand side?
If you go back to the equations,
Which left-hand side? I don't understand what.
you know all the 6 equations that you've got.
6 equation, okay. This one?
So the very 6th, it's got minus 2,500.
Yes.
All the 150 bit, and then the 0.
Yes.
But if it's all equal to 0,
Yeah.
then you get minus 5 on 2 can't equal 0.
Oh, I know what you mean. Well, okay, I know what you mean. Don't forget, I just invented this example now. No, you're right. It means what? It means, in order for this to be in equilibrium, my force T needs to be applied not in point O, in a different point, so we have a component in Z direction. Yeah, that can happen. I just invented this now, so I had no idea, right? Yeah, you're right. I know what you mean. What the colleague is saying here is that because you have 0 here, it means if you want this Z component to be 0, unless you are really lucky that this one cancels with this one, you get 0. But it means what? It means in our case we should have, or another option is, if you look at this external product here, we got 0 component here, because if we define, for example, look at this. If I define my position vector for my force P, for example, if I say, okay, my force P is not applied at this point, but my force P, for example, is applied at, let's say, this point, A, for example. This is my force P, okay? If I do like that, then my position vector is going to be this one. Is not going to be this one, so I'm going to write it here. My new position vector is going to be in the x direction, still 0. But in the y direction, I will have now 250. And then I will have 100 in z direction, right? So when I do now this cross product, I will have what? Px, py, pz. This is my force. So it means my cross product, the result, I'm going to write it here. I'm going to have in x direction, I'm going to have something like 250 pz minus 100 py. In the y direction, I'm going to have 100 px. And now in the z direction, I'm going to have minus 250 px. So it's not 0 anymore now. You can see? So before, we had a 0 in the z direction. But if I choose to put my P force in point A instead of this point here, I get now a component in the z direction. Solves our problem, right? So basically, that's what we do when we try to design the things. I just did an initial location for point P at this point. I included force P here, but this proved not to be a good option, okay? So then you go back, you put P in a different place, and then everything should work fine now. All right, so because I just invented this one, it just came up like that. But what I want you to get is how to obtain these equilibrium equations. What I want you to get is how to build this equivalent system, force, moment, everything located in one point. This is the most important thing. Then after that, you just say summation of force is equal to 0, summation of moments equal to 0. You get the equilibrium equations, you solve for your unknowns, all right? We are going to do many more examples, don't worry. You can finish now this at home if you want. And then we'll meet next week. There's just one more thing. Next week we will start the tutorial sessions. Right?